Okay, yes. I'm looking at the lecture notes reader, is that right? Yeah, page 60 you said? Okay. Okay. This is a style of question here you see on page 60 of the lecture notes for Le Chatelier, where it's a level up versus which way does it shift. If there is a change, how does it another quantity change? You're looking at this one right here, add C to this reaction. Well, if I add C, first it has to shift to the right. That's a gas, so that's an allowable state for us to do this problem. Shifts to the right, we're losing all the reactants. So A definitely will have to decrease in amount. And if it asked me, D would increase, and well, we ignore solids, so D would increase. Okay, good. Number 2. Yes? Oh, shoot, let me see if I find it again. Yes, what was your question about that? Oh, shoot, I don't remember which one is A. Okay, let's see. Here we go. This right here? Okay. For this problem, here you have a nitrogen, and here at the top, that tip right there, that's a CH3 group. So I'm comparing a nitrogen here with a carbon here. So I'm looking at the periodic table. Nitrogen is more to the right. It's more electronegative. Its conjugate base will be more stabilized, and so that will be the stronger acid. Well, when I'm comparing these, there's the CH3 there. They restricted me to the side chain, which is here a CH3 and here this. When I'm looking at those two, here the only potential for protons are the 3 hydrogens on the carbon. Here the potential for protons are those 2. There's also these. There's 2 here, there's 2 there, 2 there, 2 there, etc. So there are other hydrogens there, but for the same reason, any hydrogen on carbon is always going to be a weaker acid because carbon is less electronegative. Yeah, so that's why I picked the hydrogens on nitrogen and compared to the hydrogens on the carbon on C. Yes, the other 2 groups that are circled in green are the same. And the problem forced me to only look at the side chains, which are the parts not circled in green. Yes, the parts that are not the same. If it was including this, the main part of the chain, it would be totally different because those OH groups are exceedingly acidic in the green circle because of resonance. Okay. Yes.
Is the reason E is more acidic than B because E just has
yeah, why is E more acidic than B? And your thought is because?
Because there's more hydrogen.
There's something else going on. Does anybody know why E might be more acidic than B? Yes. Okay, several of you mumbled it. And this can have resonance. So if you lose on E, the hydrogen there on the left-hand side, then you'll have 3 lone pairs on the oxygen, which can have resonance structures throughout the ring. So you can form several resonance structures, maybe 2 or 3, at least 3 I think, within the ring itself. And so that helps stabilize, it delocalizes, it makes the conjugate base more stable, and then the acid is stronger. Yes? Which O? You mean this oxygen right here? Well, we're comparing this versus this. You want to look at if it's further. In this case, since we're comparing that hydrogen, this is identical in both groups. So you have to look at what else is there. Yes. Okay. On this also? Okay. Wow, y'all are excited. This has got more excitement than I had intended. Okay.
So for D and E, both have resonance, but why D is more acidic?
B and E?
D and E.
D and E. Why is D more acidic than E? Is that your question?
Yes.
Because here, the electron pair will be on a carbon, which is relatively unstable compared to a lone pair on an oxygen, because the oxygen is more electronegative. I'm talking about the resonance structure. Is that okay? Okay, that's fine. Okay. 3, maybe? 4? Okay, 3. Oh, what page? We're talking about practice exam. Let me flip over first. 54, page 54. This is spring 19. What number? 7. For this reaction, write the expression of Kc in terms of Kp. That's the one you're looking at, right?
Yeah.
Okay. Okay. Let's see. You balanced this, I assume. And did you get a 3 here? Okay, that's good. And so you go products minus reactants, 0 minus 3. Oh, I see what you mean. But that's for Kp. And then you have to invert it to solve for Kc. Wait, okay. I think you got it. 4. Tell me if that doesn't work for you. Yes. 57 practice exams as well. Second, let me get there. Okay. Also spring 19, number 23. Oh my. Just parts C and D. So you got solution 1 and solution 2. Determine the pH when solutions 1 and 2 are mixed together. So you've got a base and its conjugate, that's a buffer. So I'm going to use a Henderson-Hasselbalch there to do part C. pH is equal to pKa, which I look up on the back. I think it's 4.74. Does that sound right? Okay. How did I know it was a buffer? Is that your question? No, not necessarily. You got ammonia, and you got NH4Cl. This is your conjugate pair right there, so it's a buffer. So that's why I'm using this. The pKa, I just go over it's the pKa, sorry, it's the pKb is given is equal to 4.74. So you'd need to go pKa is 14 minus pKb. So it'd actually be 9.26, I think, for that. Plus the log of the base over the acid. Let me flip back to the problem. Oh, I lost the page. What page is it again? 57. The base looks like it's 1 molar, and the acid looks like it's 2 molar.
Do you have to add the volume?
You can, yeah, but it's only going to, it'll be the same on both, so it should work out just the same. What's that? Yeah. Okay. So for D, so that's buffer by itself. So you only saw Henderson-Hasselbalch. For D, I'm adding something to a buffer. It happens to be a strong acid, HI. So in that case, I'm going to take the basic part of the buffer and add it to the acid. I'm writing H3O+, but that stands for HI. If you prefer to write HI, that's fine. Because that's a strong, this is going to go forward somewhere around 100%. And then I'll get NH4 plus and, let's see, just water. I'm going to ignore water. The NH3, now I'm putting this in moles, but it was 1 liter, so that'll be easy. 1 mole. NH4 plus, that's also 1 liter, so 2 moles. And then the amount I'm adding of the HI given in the problem is 0.1 moles. So I'm going to minus 0.1, minus, okay, minus 0.1, 0.1, okay, and add 0.1. 2.1, 0, 0.9. And then I do the same thing as you see up here at the top of this, top of the screen, except the base is now 0.9 and this is 2.1. That's right, because you would divide by 2 liters, but because it's divided by on both, it doesn't matter. So if you do it, it's fine, but if you don't, you're actually okay. There's going to be, when we get to titrations, it's going to be a bigger deal. Because we won't always have a buffer, and that's going to cause a problem. But here, it's either going to divide out, or if it's 1. Now, if it wasn't 1 liter, that would have been a problem. I would have had to multiply it, more thought to the multiplication. Okay, 5. Yes, Mason. 16. Oh, oops. Okay. You see, this is my handwriting here. I wish this was up here. I don't know if that threw you. Here's what I was intending. So, let's zoom in. You said 16? Yeah, okay. So I'm going to move this in a future quarter. But I react this. That's strong. That's strong. So it must go forward 100%. You got 2 strong. So I just have water in that. What's the boiling point after it's gone to completion? What would have been a more exciting problem would be, say, okay, delta T equals IKM. And then I would go, I would be, what would I be in this case, anybody? 2, yeah, because I've got, this is ionic right there. So zoom out a little bit. 2. K, what species am I looking up to find the K value? Water, the solvent, always. So remember to look up water there. It's on the back of the exam. The molality is not given. So it'd be really funny if I gave you the molality, I think, in this problem, future exam. But for this problem, all I wanted you to realize is the concept. What happens to the boiling point, anyone? It has to go up. So the only one above 100 is that one. That's it. Okay, how you do this one, this is another classic style, same idea. That we're looking at number 6 here. What I want you to do is make a little table of each of these. I'll give you a little example. Like KCl03 versus, let's do CO2. And what I want you to do is IKM, you're going to make a table. For the first one, I is what? KCl03. 2. How about the second one? 1. In all of these, it says somehow you dissolve this, our solutions implied, in water. So this is the same as that. It looks like the molarity of each is the same, so you're just comparing the I values. Whatever has the largest I value will cause the highest boiling point and the lowest melting point. All right, you were 5? 6, maybe? Oh, there's 2 6s. You can be 6.5. You're 7. Okay, 6. Page 61, everybody. We're looking at multiple choice number 15. This is winter 19. Right here. Okay, we want to find the pH of this. It's in the calculation section, so I'm thinking probably I'm supposed to do a calculation if I have written the test correctly. We have 10 milliliters of 0.10 molar NaOH is added to 50 milliliters of 0.10 molar hydrozoic acid. Where do I find that? Yeah, it's on the table in the back of the exam. So that's why it would be, I recommend, regardless of the class, I assume they'll give you something like this. Be familiar, like, oh yeah, I've seen that word before. You don't have to memorize it, but yeah, I've seen that before. There it is, HN3. That's why I didn't give it to you, because it's right there. Okay, this is what? Acid, base, neutral. Acid, a couple ways you can know that. One, you see an H. The other, it's in the acid section on the table. Okay, Ka equals 1.9 times 10 to the minus 5. Okay. Now, it wants you to, oh, I lost the page. What's the page? 61. Okay. It wants you, I think, to find the pH. Yeah. So there's two things you're going to have to do. One is, if we're reacting these two, I'm only going to write OH minus. This has to go forward 100% because I have a strong. And so that'll form N3 minus plus water. This was, so you need to multiply these numbers. 50 times 0.1, that's this one. 5, I'll put it in millimoles, so it'll be a little easier. And then 10 times 0.1, that's 1 millimole. Ignore this, this is 0, it looks like, of that. So, is my 0 on the correct side? No, so I can't do an ice table, I have to do stoichiometry. Here's an example that's not buffers, that is stoichiometry. So, I subtract my smallest one, minus 1, plus 1, 1, 0, 4, and now what is up? What up? That's what the kids say. We have made a buffer. So now it's the Henderson-Hasselbalch. pH equals pKa, which is in the table. Go back to the table. Or you can take the negative log of the Ka, but that's too much calculator use. I don't want to wear out my fingers. So that is 4.72 plus the log of the base 1 over the acid 4. Is that all right? Okay. Yes. Did I miss something? I don't know. 61? Is that what page we're on? You're right. The total volume of the solution would be 60. So you could, if you're into it, you could do this. Some of you are, apparently, so, because I've got a couple questions on it. But again, it's a ratio, so it doesn't matter. It will matter in upcoming problems. But we haven't quite got to, we haven't done an example, at least in class, where it mattered yet. But yeah, I'm glad you're keeping track. You can always keep track and do that. You should get the same answer in this type of situation. Yes?
Why do you not just take the negative loss in the concentration of OH and then subtract that before?
Because why can't you take the negative log of this? Because that's the dominant feature. You might, it could be, if I don't give you enough of this, that this won't shift the equilibrium that much, where it's not that much of a big deal. But I don't know, that's a little risky. because this is shifting, they're reacting. If these were both bases, that's what I would do, because they're not going to react. And which base wins? The stronger one. But because the acid, even though it's weak, will cause the base to slightly neutralize, as you can see, and such that there's no base left, I think it's going to be a big deal, is what it seems like, because there's no base left.
So the fact that there is an acid usually cannot find a POH?
Because there is an acid, yeah, because they're the opposite, one's an acid, one's a base, I would do this first. Now, you could have been right if this was 5 and this was 1, you'd dominate in the amount of hydroxide, and so in that case, you'd probably be correct. But because I made the weaker one more, then it's actually making a buffer, so I believe the pH would probably change significantly. Okay, 7? Wow, I don't know if I can get to 11, we'll see. Oh, I don't know. It depends if they're quick, because we have like really... Oh, it was related, yeah. Okay, spring 11 is where I'm turning to now. Number 20. Okay, this is page 96, yes? Spring 11, number 20? Oh, number 21?
Yeah.
Okay. Yeah, okay. Page 96, everyone.
The same thing, but there's not a rapid decrease, so I don't know
Which one are we doing? Add A, increase volume, or add B? Add A. Okay, so we're looking at this one right here. This one. Add B. Oh, and did you get no change?
Yeah, the answer D said no change.
Ouch. What is wrong with me? Anybody? We got no change. It's a solid.
Oh.
Yeah, so solids are not going to affect, and liquids are not going to affect this. That was your main question? Okay, cool.
And,
Oh, wait. Depends how long this is. Because number 8, 9, 10, and 11 will gang up on you after this. Spring 11.
Number 6, spring 2010.
Spring 10.
Yeah.
I don't have a spring 10. Yeah, I have to. Every year I cut off some because it just gets too ridiculous, the number of exams in here. So, what number?
Number 6.
Number 6. So most of you don't have this one. This is an indicator. Estimate the pH of phenol red. Okay, so this is an indicator. It is indicated as yellow below 6 and red above 8. So its pK of the indicator is likely somewhere in between that, where it changes between red and yellow. So probably more like 7, I would guess. Does that make sense? Yeah, that's it. So the color change happens at the pK of the indicator. Indicator is typically an acid, so you would just look anywhere in between. Yeah. Okay, 8. Yes, oh, wow, okay. It does.
So there's 2 indicators?
Yeah,
So are they cool from the specific?
yes. I mean, they're equivalent. Can I show this to everybody? Is it okay? They'll see your, okay. This molecule, but imagine no hydrogens here. But they are there, but there's one missing right here. So there's 2 hydrogens in the center, 3 here, 3 here. Where's the most acidic hydrogen? It'd be the one in the middle contributed by both sides that have the most resonance structures. So they're both equivalent. So you can't tell the difference. They're like identical twins. So whichever one is lost first.
So if you took one,
No, you just pick one. Yeah. So either one of those hydrogens, those would be the most acidic. Yeah. But you can't lose both because that would make it's harder to, much harder to lose the second one. Yeah. Okay. 9?
Please answer.
Oh, cool. Wow. Thank you. 10? 10 and 11, thanks you. 10? Oh, up here. And then 11 over there? Okay.
Spring 16, number 13.
Spring 16. Let me see if I can find that. Spring 16. Okay, we're looking at number 13 on Spring 16. So that's page 74. Zoom out. Wait, I forgot you said 13?
Yeah.
Okay. So, acetic acid. Okay, so this one I was actually super nice that I gave you this hint and that reaction and this reaction right there. I wouldn't always give you all that action. So we'll just focus here on this reaction right there. That's the one to find the K value for. Let me write that down. So I give you in this question this reaction. Let me write it down. There it is. Okay, I give you this reaction and ask you for the K value. First of all, let's game the test a little bit and not try to do any work, okay? Do you expect this K value, anybody, to be large or small? It's large because what? This one right there, that's strong. So I expect it to be fairly large. So right now, I'm looking at A, not B, maybe C, but it's not as big as I'm hoping for because I'm like large, strong base near infinity. So A or maybe, is that a positive on D? Yeah. Yeah, A or D, but D is KW. So that sounds really ridiculous. Just thinking about it, probably A is it's the most reasonable answer. Now you can do the math. I would say at the end of the test, I would circle that one, come back at the end of the test, and start doing your work. So I gave you hints, but you wouldn't need those hints. You would see acetic acid. So this is basically a Hess law question. So you write the Ka for acetic acid. And this has a Ka. Okay, that's given on the back of the exam. And then it gave you the hint of the ion product water, or just like the other one when we're doing that baking soda equivalent problem. Kw is a common type of reaction to use at this moment because you need to switch from H3O plus to OH minus. So whenever you need to make that switch, this is a good one to use. Okay, so I want to ask myself, how can I go from the brown reactions and add them to get up to the blue reaction up top? Well, this matches here, and this matches here, so I'm not going to mess with that one. However, this one, I need this OH here, and I need a water here. So I'm going to flip this one. Times by -1 or raise this to the -1 power. So the mystery K for this reaction is equal to Ka, if I add these two reactions, times Kw to the -1. Is that alright? So that's how you mathematically do it. Alright, 11. Hi.
Oh, sorry. Okay.
Hi.
Okay, I'm sorry. I was like, oh, that's
I know, I'm mind blown, right?
No.
Okay.
Can you talk the colligative properties overview?
Oh, a little colligative properties action? Okay. Let's do a little overview and then maybe some recommendations for the exam. Okay. First, colligative. Pi equals IMRT. And then the other one is the delta T equals IKM. Okay. There's two styles of questions to ask if it's math related. The two math related questions, one is just straight plug and chug. So for example, I give you M, R, and T. I comes from the molecule, and you calculate pi. That'd be a really easy style question in my mind. One level of difficulty up would be to ask you something related to the concentration unit in both, in either reaction, depending on either equation. So something here or here. If I wanted to do that, that would be something about an amount, a molecular formula, a molar mass, something of that nature. Okay, we did one with sulfur, I think, in class, if you want to look back. So that would be finding the concentration and then converting to the unit that's requested. Okay, that would be a little bit more difficult, but those are generally not very difficult questions. I'd say for most people, sometimes the multiple choice on these is harder. And that's the conceptually based questions. So my recommendation is to look through for sure some of the multiple choices on these. For example, we did actually one, I was asking you, what's K for? And a couple different ones. It's usually water if it's aqueous. It's the solvent, not the solute. That's a common mistake, is to think it's the solute. Delta T is going to be for the solvent or the solute? The solvent. Usually water, if it's aqueous, because that's what there's more of. The solute will cause the solvent's boiling point or melting point to slightly change. So this equation, and so if I could recommend a page to review here, as far as that goes, there's other kinds of multiple choice questions that we asked. We did one for Mason, I think it was is basically figuring out which I is the largest. Is one way to put it, but I'm going to refer you, make sure you review down here, what does each variable refer to? This is page 52 of the reader, and make sure you got if it's a solvent or the solute or what the heck I'm talking about, okay? For example, I is always the solute, so you need to just get it all straight, and that's common, easy to get tripped up on a concept question because of that. Okay. All right, let's close it up right now. I will see those of you in my class. You're not in my class, you can come to my class too, I guess. But I will see most of you on Tuesday.